Today we're going to cover text entry. And then on Wednesday, I'm actually out of town. I'm leaving tomorrow morning really early to go to LA. And Jeff will be talking about ergonomics and human factors. And then next Monday, I was able to arrange another guest lecture, Ted Selker, who's a real wild man. He invented the pointing stick in the middle of Lenovo's IBM laptops and a bunch of other things. And he's a real dynamic guy, and he's always a lot of fun to hear from. So it'll be interesting to see what he talks about. Hopefully we can rein him in a little bit and hear some stuff that's relevant. Then on Wednesday of that week is the midterm, and it'll be in class, so it will be about 80-minute test. I'll design it to be about 60 minutes, and hopefully everyone can finish on time. It'll be generally the same as the in-class tests, the quizzes. A little harder, more fill-in. It'll cover the material in all the lectures so far and the first two homeworks. And homework 3 is actually due next Monday. So hopefully everybody's making good progress on that. I'll be on email, so if you have questions, you can put them in Piazza. Jeff has office hours this afternoon. Unfortunately, he wasn't able to finish grading the homework quite yet. It'll be available today after 4 if you want to go to his office, or I'll bring it to class on Wednesday. Or he'll bring it to class, I guess, because Al won't be here. Then you have spring break. And then right after spring break, homework 4 is due, and then we'll start on the projects. So we'll talk about, we'll spend some time on this class talking about the projects and talking about the groups and what you want to do, but you might want to be thinking about, what sort of things you have in mind for your projects. There's the list on the first page of the course website with some ideas, and we'll certainly be interested in other ideas. Remember what an interaction technique is. A few people who've emailed me ideas really weren't interaction techniques. It was more like, let's design an application to do something. And that's really not an interaction technique. So it has to be reusable. It has to not be a particular application, but rather something that can work in lots of different places. Do you have a question? Well, okay, we'll try to do that. One of the questions, the reason we haven't done it already, since I'm covering the material for it today, is that we're not quite sure what the test harness is going to look like, because we haven't finished implementing it yet. I keep finding all these great test harnesses in C# and Java and all these old languages, and so we have to reproduce them in JavaScript to make them work across platforms. So if we can get the whole thing implemented in the way we want, then we'll have a much more comprehensive assignment. But hopefully we can get that done quickly. Okay, and so that's kind of what I wanted to cover. So homework 4, you're supposed to start this Monday, next Monday, and it's on text entry. And so that's what I'm going to be covering today in class, so that we're ready for it. So we're covering it a little early, which is better than covering it a little late, I guess. So this is all about text entry. Surprisingly long history with lots and lots of research and lots of inventions. This is an old-fashioned typewriter with kind of an unusual arrangement of keys. So the topic includes a little bit about text editing. I'm really not going to cover almost anything about text editing. We talked about that to some extent when Larry Tesler was talking about copy and paste, when David Smith was talking about the kind of editing that he found, and we also talked about moded editing and using different kinds of control keys. How many people use Emacs? Nobody? A couple people? How many people know what Emacs is? Good. So there's two popular editors for plain text amongst programmers, I guess pretty much only programmers. One is Emacs, which was invented in the 70s and is still pretty much the same as it was then. And the other one is based on Vim, VI, which was a visual editor for Unix. Now it's called Vim or something equivalent. And the main difference, Emacs is a modeless editor. You're always in edit mode. All the operations are with control keys. There's lots and lots of different ones. And they're a totally different set of control keys than we're used to. So Control V in Emacs scrolls down instead of doing paste. And the nice thing about Emacs, I like Emacs, is because you can write macros and you can do all sorts of programming in the editor itself to make things easier for you. But if anybody's interested in editing, text editing, that would be a good project. But we're not really going to talk about it very much anymore. But there's an awful lot to say about text entry, typing, getting data into a computer. This is a comic from 2003 when the Palm Pilot was starting to be popular, and it was kind of getting at this idea that we're scratching on tablets just like we did in prehistoric times. We went to typing for a while, and then we're back to scratching on tablets. So the first thing I want to cover, just in case I don't have enough time to cover everything in this lecture, are the two key points about text entry, the two key aspects. The first one is obviously speed. How fast can you enter text with this technique? And there's a variety of different measures, but almost everybody eventually comes down to something called words per minute, WPM, and that's standardized to 5 characters per word. I don't know what they do in other languages, but this is in English, it's kind of the average length of a word. And so all of the measures are standardized to 5 characters per word. You could also imagine there being a characters per minute measure, which is basically a factor of 5 off from words per minute. But everybody uses words per minute. And kind of the standard target for how fast you're supposed to enter is around 40 words per minute. And that's what most programmers can do if they're just typing. Does anybody know what their own words per minute is? Anybody faster than 40? Anybody? How many people know touch typing so they don't have to look at the keyboard? How many people still use 2 fingers? So my wife still uses 2 fingers. She's pretty fast, but she completely ruins the keyboards by whacking at them really hard. So 2-finger typing tends to be around 25 to 35 words per minute. A professional typist, anybody professional typists get 100 words per minute? If you're trained and practice a lot, then typically you can be over 100 words per minute with touch typing. The fastest, according to Wikipedia, is around 200 words per minute, which is pretty impressive on a conventional keyboard. Court reporters, if you've ever seen them, they have this really interesting keyboard, and that goes up to 225 words per minute. The highest recorded speed for court reporters was 375 words per minute, which is really amazing. Handwriting is way down in terms of speed. Handwriting is quite slow at 22 to 31 words per minute. So if you're handwriting notes on paper, that's kind of the speed that you're getting. But what about talking? So I'm talking at about 100, 150 words per minute. I'm trying intentionally not to talk too fast. And so audiobooks and other kind of public speaking generally try to target about that speed. So if you're handwriting, you're never going to be able to write down everything I said, for example. But if you are a professional typist or a court reporter, obviously that is within the range of what they're able to do. So that's part of the, obviously, goal of court reporters is to get everything that everybody says. Really fast talking, like in auctioneers or ads on TV where they talk really fast, is around 250. And the fastest recorded talking was 637. words per minute. I don't know how they could possibly detect that. And I don't know if you can really understand words spoken that fast, but that would be another interesting device. And what we're going to see as we go through the rest of this talk is text entry techniques for mobile devices, and a lot of alternative devices are substantially slower than most of these speeds. Okay, so 40 words per minute is our target. But if you're talking about, speech, we're at the range of 100, 150 words per minute. Another measure for speed that was introduced by McKenzie. So there's this guy, Scott McKenzie in Canada, who's one of the world experts on measurement of speeds and errors. And so a lot of the references you see will be to his work. And I just wrote him about the stuff we're doing in this course, and he was sad that we weren't being a little more formal and a little more, systematic about the measurements. And he said the tool that you guys used for assignment 1 was just too primitive, and we should have measured all these other things. And I said, well, that would be good if we had the whole semester to deal with it. And he said, oh, well, his students, they're CS students, and they all have engineering degrees, and they can do it. And it's like, well, we didn't really want to go to that level. Anyway, he introduced this idea of keystrokes per character. And if you think of conventional QWERTY keyboards, if you want to type a Q, you hit a Q, so it's clearly 1. On the other hand, if you want to type a capital Q, you have to hit the Shift key and the Q, so that's 2, right? And so if you average over all the keys on a keyboard, it's like 1.001 or something like that, right? So most of the time you just need 1 character. On the other hand, if you think of other techniques, you may have to hit a bunch of different keys at the same time, or one after another, in order to generate the characters you want. So it doesn't help to type really fast if almost everything you type is incorrect. And so the next measure is errors. And then my former student Jake Wolbrock and I wrote kind of the definitive paper about measuring errors. And this is based on Scott McKenzie's work and some other people, but basically extending it to be a very systematic way of measuring how many errors you're making when you're doing text entry. And this is a required reading for the homework and for this class. And hopefully we'll be able to get some of this content into the assignment. Basically, the idea is that there's uncorrected errors. So if you look at a document and you see a typo in it, that's clearly an uncorrected error. The user typed something, gave it to you, and you can see that there's still an error in it. So those are errors that you miss, that are left in the final document. And so typically, people notice when they type something wrong, and so those are typically fairly low, the number of uncorrected errors. There's probably a lot more in, informal writing or in emails, especially also in, text. If you're text messaging, people don't care about uncorrected errors so much. But in formal writing, you get numbers like 2% or 0.79%, so very low numbers of errors that are left in final documents, especially if you have time to proofread them. On the other hand, corrected errors are when you're typing along and you see something wrong and you hit backspace and you fix it, right? And it turns out that if you look at the statistics for typing, then backspace is typically the second most popular key, sometimes the first most popular key. So when we were looking at programmers, like 10% of all keystrokes were backspace. So people are doing backspace an awful lot, sometimes just because they're typing and they make something wrong, or else they explicitly change their mind about what they want and they use backspace to remove it. So corrected errors, if you're doing a timing test and it says type this paragraph and you're starting to type it, until you hit the final return that says you're done, then if you do backspaces while you're typing, then that counts as part of the whole total time, right? So corrected errors generally are part of the time measurements of how fast this text entry is. And so you end up with kind of this, what you might call aggregate measure. It's measuring both the speed at which you can enter stuff as well as the speed at which you can notice and then correct things if you do something wrong. And so corrected errors are generally kind of built into the words per minute counts that you see. And obviously, if you can enter text more accurately and don't make any mistakes, then the WPMs are going to be faster. And an error-prone method tends to be slower. But what Jake in my paper tried to do was actually pull out these corrected errors and measure those as well. And that's because there's a variety of useful information you can get by looking at the corrected errors. So you kind of would like to know, is my text entry technique error prone? So that, you know, if everybody just is very accurate and corrects all their mistakes, then you can't necessarily tell if you have a very error prone method. Another thing is that people will often type an incorrect character, then a bunch of correct characters, and then notice that they have something wrong, and backspace the correct characters in order to get to the incorrect character, because that's just the fastest way to do it. And a naive measurement would count all of these correct typings as errors because they were deleted by the user. And so the idea of measuring exactly what's actually wrong will help you have a better measurement of what's accurate and inaccurate. And there also may turn out to be some characters that are just hard to type or hard to enter, right? So if on a regular typewriter, people's little finger is always hitting the wrong key, or in some gestural alphabet if something is hard to do, or in a soft keyboard like on the iPhone, if one of the keys is sticky or tends not to be done correctly, then it may turn out that there's this one special key that's giving you the wrong data and you want to fix that. And so you can't tell that if you don't have this idea of what people are actually correcting. And then there's also the ability in many situations to end up with what we call a no recognition or a no character. So if you're thinking about graffiti where you do a little symbol or handwriting, it may turn out not to recognize the thing you draw and beep at you, right? So I do this thing and it says, no, I don't recognize that. Nothing happens. Or similarly, on the iPhone keypad, you might tap somewhere between characters or above the keyboard and nothing happens. And most times you just ignore that and keep going on, but still that might be something you'd like to know, that there's this problem that some things are not being recognized. So we came up with this algorithm that tries to match up what's actually typed. So P is the presented or target. Well, P is presented and T is what people actually type. So this is obviously an uncorrected error, so this is an error in the result. But IS means the input stream, and that's what the actual typing as you went along was. And in this case, we typed a Q and then a V and then a backspace and then a W and then a backspace and then a U. And then the resulting string will be exactly the same as presented. So in this case, there are no uncorrected errors, but there's 2 corrected errors. And you get the sense that the user is having a hard time typing the U because they typed a V by accident and a W by accident, but they noticed it and backspaced over it. So that's a substitution. Because they substitute one for the other. In the presented string up here, there's this interesting question of whether the KLY was typed correctly. And you just kind of assume it was, even though it's in the wrong position, right? So instead of QUI, there's QU, and then there's a missing I, and then there's a C, and then there's these 2 extra things. So there's a question of, what did the user intend? Did they intend for the C to be the C, or was the C when they were trying to type the I? You can't really tell, right? Because you can't read the user's mind. All you can see is what actually came out of their fingers. And so the idea of this algorithm is to try and match up these 2 strings as closely as possible and tell you whether it seems like there were incorrect letters inserted, there were some important letters that were missing, so these are insertions, omissions, or the wrong characters were typed when they meant to do something else. And so by looking at the resulting string and doing this matching to try and match them up, you can come up with a measurement of how many of each kind of these errors happens. And they can be corrected or not corrected. One of the interesting things about the algorithm, which is not true about lots of input techniques, is that the backspace itself is really reliable. So on a keyboard, probably every time you want to hit a backspace, you do, and you rarely hit something else by accident. The backspace is nice and big, it's in a special place, and people rarely type the backspace by accident on a keyboard. On the other hand, on the iPhone, I'm always hitting the backspace by accident or hitting something else when I mean to hit the backspace. And so this algorithm does not have any way of recognizing that problem. So it might be interesting if anybody's really into math or pattern matching or anything like that to think about what you could do about coming up with an algorithm that takes into account when backspaces themselves can be incorrectly hit, because it's pretty hard to detect what's going on. The other thing that this algorithm generates is what it calls a confusion matrix, which helps you understand if I'm trying to type one character, do I frequently get a different character? And that might be useful depending on your keyboard or your input technique to know what sort of errors people are making. Because if it's the key that's next to the key that you're trying to hit, then maybe you can adjust the key sizes. Or if it's a gestural recognizer that's misrecognizing a lot, maybe you can fix that. So this is what the algorithm produces, and when we're looking at input techniques now, we're going to want to know what's the words per minute, what are the errors in terms of both corrected and uncorrected errors, and can we detect whether those errors are one of these kinds, insertions, omissions, or substitutions. So that gives us a little more scientific basis on measuring different kinds of input techniques without just saying, oh, it seems nice, or it seems fast to me. And two other things to keep in mind. So some of the techniques we're going to talk about have a recognizer built in. So that's when the user does something and the computer has to figure out what you meant. Okay, so that's like a gestural alphabet. So this is the graffiti alphabet, and when I do this, it's supposed to recognize an F. So if I do this sloppily, then it may recognize something else by accident. If I do it carefully but too slowly, there are all sorts of ways the recognizer might misrecognize what I type or what I enter. With a keyboard, physical keyboard, there is no recognition errors. The user could type the wrong thing by accident, but whatever the user types, the computer is pretty much going to recognize. But there's also the separate issue for recognition systems that even if the system recognizes it exactly, the user may just forget which one to enter, right? So in the graffiti for the Palm Pilot, there are these 4 strokes which are all kind of L-shaped, and each one generates a different letter. And you might say, oh, that's really obvious. L is like this, and J is like this, because that looks like a J. But maybe F and T aren't so obvious, right? And once you have all 4 of these, you can certainly imagine forgetting which one is which. And even though normally you wouldn't ever forget what an L looks like, given that you're supposed to memorize all these, you might get them mixed up and enter the wrong one by accident. So even if the recognizer is really accurate, the user may have a hard time remembering which is which. And then the next thing that happens, of course, with a lot of text entry techniques is auto prediction and auto correction. And these are slightly different. Prediction says I haven't typed everything yet. I've just typed the prefix, the first part, and the system's going to guess the rest of it. Okay, and both of these happen on the iPhone. If I start typing watch, then the system's going to say, well, there's not very many words that start like that. Maybe he means whatchamacallit. And if I just type a space now, it'll type the rest of it for me. As opposed to autocorrection, where I finished typing the whole word, but I typed it wrong. And in that case, the system is going to try and help me fix those errors by proposing an alternative that's different from the one I typed. And so many systems combine these, but it's important to remember what the difference is, because there are systems that only do one, or it does one better and the other one not so well. Okay, any questions about kind of this background before we get into this long list of actual systems? Okay. So we're starting with mechanical typewriters, and so there's a very long history of these. The first successful one was invented by a guy named Christopher Sholes with some other people in about 1868, and he actually invented the layout, which we now call QWERTY, Q-W-E-R-T-Y, as a way of trying to help with a mechanical typewriter keeping the sticks that are connected to the letters from hitting each other. How many people have seen a physical typewriter with little hands? Okay. I certainly recommend the rest of you go and look at one in a museum. They're really interesting. Basically, the idea is when you push this down, there's a lever, and there's a stick, and on the end of the stick is the backwards drawing of the key, and it hits a piece of ink, which then hits the paper and prints that on the paper. So the goal of having this weird layout was to try and make sure that you didn't have two of these sticks coming up at the same time, because that would tend to jam the machine. And when I was little, I certainly typed on these kinds of typewriters and got them jammed all the time. So Sholes patented his idea and his layout and sold it to Remington, which at the time was a sewing machine company, so they were very expert at making machines, machine tools out of metal. And so they produced this typewriter, and it became very popular. And they also introduced the name typewriter as a name for their invention, and it became really popular. And this is still the layout we tend to use today. Foreign keyboards have slight changes. Anybody have a French keyboard or some other foreign languages that has a different set of keys layouts? No? Huh? Not anymore, yeah. So I don't remember. So what's, do you remember what your keyboard has? Yeah. Where? Here instead of M? Okay. Right. So there are lots of extra letters in foreign languages. So Spanish has the ñ and the double R, and okay. So they don't have to have that on the keyboard because it's easier to type. And there's a variety of other special characters in other languages. Yeah. I'm sorry? Where? Oh, really? And that's for what language? For French? Yeah. There are a variety of other key layouts for English. Yeah?
So I'm just curious about how did they define the position of keys? Because key is like the most common, but it's still not
Yeah, so there's a variety of stories about that, and you can look them up on Wikipedia. But the general consensus is that what he was trying to do was make sure you didn't hit two keys at the same time that would jam. And so he wanted you to alternate hands and not tend to do two keys that were very similar. So it was specifically not designed to be fast. It was designed to try and separate out the letters to be far apart. Yeah?
Correct me if I'm wrong, but wasn't the idea that it was only a problem with jamming if you had two that are next to each other go? So with the two hands there, he was wondering, not because it's slower, it's actually fast because when your hand is tapping, the other one can move independently. But you're alternating so that the adjacent ones don't jam.
So near the top, so all of these come together into a point, into the one place where you're typing. And so at the very top, it has to be one at a time, obviously. But down here, they start off real close together. So It's definitely worse if you hit 2 of these at the same time because they'll get jammed on the way up. But at the top, you could theoretically have 2 of these moving at once as long as one gets out of the way before the other one gets up there. So there's a variety of questions about whether this keyboard achieves that result or that's really what they were going for. Apparently, this information has never been definitively known. So Dvorak, a few years later, invented a new layout which was specifically optimized for English to try and make it really fast. And so this one used letter frequencies and what's called digraph frequencies, or the most common 2 letters that go together, in order to come up with a layout that was, in fact, generally agreed to be much faster. And they also recognized that, like, your little finger is the least strong, and so they didn't want to put the most popular letters on your little fingers, or reaching down is slower and things like that. So you theoretically like the most common letters on your home position, and so forth. And so this one became an ANSI standard. It used to be that you could switch your keyboards over if you wanted to. I had a staff person working for me once who actually learned to type this way, and whenever I tried to use this computer, all the keys came out wrong, so it was really confusing. But does anybody use this? Recently, I haven't seen anybody who's trying to use this anymore. This is the keyboard that court reporters use. It's called the stenotype machine, or stenographer's machine. And there's a surprisingly small number of keys on it that typically are not labeled. And the way that you type with this is that you push down chords. So you're pushing down multiple keys at the same time. And the chords actually represent entire words. So the is one press. And most words can be done, or small words can be done in one single press. And it's actually phonetic. So you basically are doing syllables. And so it actually is quite old, and the original versions printed on paper tape. And then those would be manually transcribed onto regular words. Nowadays, of course, they just plug these into computers, and it comes out with real words, and then they go back in and type. Usually when somebody stops to take a breath, then they'll quickly look up and edit the contents to be more accurate. So they're still in use. If you ever go to court or you do a deposition or do anything legal, then you'll see that there are people here using these now. And they're really amazingly fast. I was actually doing a deposition with a guy who was one of the world record holders in terms of typing speed, and he could even he could keep up with what I was doing. And he also had such a good memory that he could stop and do something for a few seconds and then catch up. So he could go substantially faster than I was talking, and he had a really good audio memory so that he felt like he could be doing something and still remembering what I was saying. So that was really impressive. You get way behind and then he'd catch up, and it's like, whoa, how did you do that? So what about other techniques for text entry for regular computers? The only thing that's really significant is this Engelbart key set that we've talked about a bunch of times, which has 5 keys, so that's only 2 to the 5th values, but you can't use all up because that would be silly. So there's 31 possibilities, which isn't enough for all the numbers and letters, so they just use it for the letters. And they had a mode switch that would do numbers. There are obviously a variety of on-screen keyboards. There's techniques for foreign languages, which we're not covering. And there's a long history, as we talked about before, of handwriting and tablets and stuff like that attached to real computers. But really, most of the interesting effort has been with handhelds. This one is a really fun technique. It was designed for handicapped people, but it works with regular computers and handheld computers and stuff like that. And the basic idea is that all the letters are squished up at the right side of the screen. And as you move your cursor over there, it uses a language model to guess which letter you probably want based on what you've typed so far and what are the most common letters to follow. And so what he thinks you want will get bigger. So here I've typed TH, and you can see that A, E, I, O, R, and U are the most common things it thinks I could possibly want to type next. And so those are really big. There was a question? And so as I move my cursor over to the right, those will get bigger, and then it's a lot easier to hit those. And all these letters are swimming at you all the time. So it's really very dynamic. And so it's easier to tell from a video. So let's see if this works. So as you move your cursor over, obviously when you haven't started yet, they're all equally likely to some extent. But he's in the general area of H. Okay, and so the most likely things are vowels after that. So he goes to the E, and then L, and some of the other letters. And if he didn't want an L, then he'd move to the left and get out of the way. And if you're really sure of what you want, then you can move further to the right to make it go faster, or to the left to make it go slower. So we've got hello. And if I want to do how, then it's pretty straightforward. I just move quickly.
Did you ever click?
You don't have to click. You're just moving. You're just in the vicinity. And if you want to go backwards, you just move to that way in order to stop things happening or to slow it down. So you can tell that this can be pretty fast. This is slowed down a little bit for video. It can be quite fast, but it's very intense, right? Things are swimming at you all the time, and you have to really pay attention. If you stop paying attention, then things ended up going haywire. So it's called Dasher. It's a pretty interesting little technique, and I put it here in the talk because it's like the only significant research that I found that has anything to do with text entry on PCs, except for things for the handicapped, and we're going to cover those in a different lecture. What about autocorrection? Certainly, we're all familiar with the Microsoft Word techniques. It has two totally different techniques that it uses. It has autocorrect from a list, and there's this enormously long list of common typos that it's willing to do automatically for you. And you can go look these up. You may not have ever noticed that they're there. And you can add your own shortcuts to this. So I've done that occasionally. If there's some word I type a lot, then you can add some shortcut, and every time you type the shortcut, it'll replace it with the thing you want. So here's an example, actually, where I put in a shortcut, TPP, for the 983 and 342 patents. And there was a time where I was typing this so often that I just figured I'll add my own shortcut, and then every time I type TPP space, it would replace it. But mostly it's supposed to be for these kind of typos like totally. Separately from that, and separately from that is the squiggly underline that we're familiar with, the typo correction. And that was introduced in '95, and it's based on a dictionary. And so it doesn't change it automatically for you. It just leaves it in the text, and it gives you a pop-up menu where you can say, yeah, this is the one I want, or no, I know that's correct, so stop telling me about it. Or not only do I know this is correct, but I want you to add it to the dictionary because I'm going to be typing this in the future. And so it doesn't do it automatically. You have to do it manually. So that's very different than handheld devices that tend to do these kind of things automatically. Interestingly, these autocorrects and the spelling check fixes are both added to the undo stack. So if it does something wrong and you don't like it, then you can always hit the undo key and go backwards. So if I type transparent and if I type totally wrong and it automatically fixes it to totally, then after the space is entered into the stream, this autocorrect is entered into the undo stack. So if I hit undo at that point, it'll go back to totally spelled wrong. And then if I hit undo again, it'll erase the space or erase the Y. So you end up with, actually it puts the undo after this, in the stack before the space. So you end up with things in the right order. So it actually, mucks around with the command history in order to put all of these corrections into your history. How many people have used that feature, the undo of the autocorrects? It's a really useful thing to know about. Okay. So most of the research has been on portable devices, and so we're going to talk about that for the rest of the lecture. These are a really enormous variety of different ways of doing text entry on things that don't have a regular keyboard. And so we're talking about pads, tablets, phones, smartphones, kind of anything with a screen that doesn't have a keyboard. And kind of the general goal is to make it so that if you wanted to type at 40 words per minute or whatever you're used to with a regular keyboard, you could approach that kind of speed. And obviously, you kind of want a reasonable level of accuracy because it's really annoying when it does it wrong. And another requirement is often that you don't want to have to require people to make a lot of practice, to have to do a lot of learning. And so there's been a bunch of approaches that people have tried, which turned out to be relatively fast, but required weeks of practice, and nobody wanted to do that. And so that's a trade-off that you can imagine is fairly common, that if you want to make people effective, but they have to practice a long time, versus maybe it's easier to learn, but maybe slower in the long run. Another interesting observation is there's a very different purpose for most text entry on portable devices. So when you're writing a formal paper or a homework assignment for this course, you probably prefer there not be a lot of typos in what you're producing, and you're willing to spend an extra amount of time proofreading and fixing things, as opposed to when you're sending an SMS or a text message. SMS is the formal name for text messaging. It's called short message service. So when you're sending a text, you probably don't care too much about typos, and if your meaning comes across, then it's probably okay to send it out like that. So you may not be as careful or care as much about typos. And on the other hand, if you're entering an address or a phone number, then it's really annoying if it gets it wrong, because then it doesn't work. So there are these kind of different needs that you have for text entry, and sometimes you can take those into account when you're figuring out how much accuracy do you need, how much speed do you need, and things like that. So some of these slides are basically directly from the previous talks where we were talking about history, but I wanted to put them back in here so that everything's in context. So we already mentioned the Park tab and a few of the other systems we're going to go by. The Park tab was this little device, if you remember, that was invented around '89, and David Goldberg invented this system he called quick writing, where you would do the strokes directly on top of each other. And so the idea is that you don't have to move, unlike handwriting where you go across the page. You just do things on top of each other. And he designed the strokes to be as small and fast as possible. So horizontal stroke this way means something, and horizontal stroke the other way means something else. And diagonals up and down. And he designed them based on frequency. So the most common letter is E, so that's very easy. T is very easy. R, I, A. Okay, whereas Q is really unusual, and so that one's a lot slower to enter. And so these strokes are very easy to recognize, so the computer is not going to get confused, and most people will draw them accurately. That was the goal. And so the quick writing turns out to be quite fast to enter, but of course it requires a lot of time to memorize all of these strokes and which one goes with what. And so that's obviously a big challenge with this, that memorizing that E is to the left and T is to the right, it's just a lot of trouble. They got a patent, Xerox got a patent on this technique, single stroke called unistrokes, because everything is one stroke, on unistroke text entry on top of each other, and they successfully asserted that against Palm's graffiti, which we'll come across later. If you remember, there was this whole excitement about tablet computers and pen-based computers in the early 90s, late 80s, early 90s, and one of them was PenPoint. And if you look in the manual, you'll see that they teach you how to handwrite letters accurately so that it can recognize them. So you're hand printing, it's called printing, where you separate each letter very carefully so it doesn't have to try and figure out the letters, and it shows you that, you know, this one is not going to correctly figure out that that's an H because it looks like an N. Here the R is separate with a little gap, and so that's going to not work, things like that. So it's trying to teach you all these correct ways of doing things so that they'll be recognized well, and so it, or ones that it will make mistakes. Microsoft in '91 came out with a handwriting recognizing Windows version for tablets, and so anytime you wanted to do text entry, instead of using a keyboard, it would pop up this little dialog box, and you'd write into the dialog box, and it would throw the characters into the application that's behind it. And so it was a reasonably good handwriting recognizer. Obviously, you could do a better job today, but you know that was 13 years ago. But it really was not particularly accurate, and it was really hard to correct things when it got things wrong. So they didn't do a very good job of error correction, and of course it's going to be wrong sometimes, and that's really a big issue with a lot of these systems. We talked about the Apple Newton, which came out around '93, which also was a handwriting recognizer and had historically really bad handwriting recognition. It also had a pop-up keyboard, and it also had autocomplete, and it had a recognizer that can do hand printing. But nobody ever talked about those. Right? Everybody was focused on the handwriting recognition, which was relatively error-prone, and also not very successful. Okay. So those I'd already covered, so I just went through them really quick. If anybody has any questions about them or wants more information, let me know, or you can go back to the previous lecture where I covered them a little more thoroughly. Text entry for phones is obviously a long history. Why do we want to do that? Originally, it was for SMSing or text messaging, which actually is surprisingly old, predates the internet, and wanting to use the things on phones. But you know, then people quickly realized that they wanted to use the internet on your phone, and so you needed text entry for that as well. And so there were a variety of reasons that people wanted to do text entry. And so this is a graph. I couldn't find one for the US, but this is from the UK, of a graph of how many text messages were sent per year. And the UK, it got to be popular around '99. This only goes to 2003, where it's 20 billion text messages per year. I'm sure it's a similar graph for the US. But anyway, you're getting this kind of exponential growth of the number of text messages. But it starts, you know, not that long ago that people were doing this. So how many people have ever used a, who knows what this is, right? What's this?
Rotary phone.
It's called the rotary phone. It was invented around the 1920s. Okay, so that's quite a long time ago. Well after, you know, Alexander Graham Bell formed the Bell Company, which was called AT&T. And they, in the original dial phones, put letters around some of the numbers. And these were called exchanges, and they were to help people remember phone numbers. Okay, so CMU's exchange is 268. That's the first 3 digits. Who knows what that spells? Right? It spells CMU. 2 is C, M is 6, U is 8. Right? So back in whenever the university first got their phones in the 20s, right? We were founded in 1900, so in the 20s when we started getting our own phone numbers, it was CMU 1000 or CMU 5150. And so that's how people would remember their exchanges. And typically they were pronounceable, right? Or that they would represent something. So Squirrel Hill is 521, things like that. So why isn't there any numbers on the 1? Who knows why there are no numbers on the 1? Yeah? No. Who, yeah? It is, the country code is actually a newer reason for it. Who knows why? Anybody? Any other guesses? So in the past, if you wanted to make a long distance call, you had to dial 1 first, right? Which is the same as kind of the country code. So if I wanted to dial, if I was in Pittsburgh and I wanted to dial New York, I would dial 1, and then 212 was the area code, and so forth. Our area code is, what's our area code? 412, right? Originally, all the area codes had a 1 or a 0 in the second digit. Now they're a little more flexible. But originally, but you couldn't tell the area code from just a regular number without the 1 in the front. Because in the olden days, they wanted to know before you started a number what you were doing. So you'd have to dial 1 if you wanted to dial long distance. And so none of the area codes, none of the exchanges could start with a 1, because 1 meant long distance. So if I'm dialing Squirrel Hill, or if I'm dialing downtown, or if I'm dialing Monroeville, all of those would be in the 412 area code, and none of those would be long distance, so they all had to have exchanges that started with one of the other numbers. And why isn't there any numbers on the 0? Why aren't there any letters on the 0? Right, so if you dial 0, that's always going to be the operator. And so, again, there would never be any exchanges that started with a 0. Because as soon as you dial the 0, you get the operator. So 1 and 0 were special numbers that you could not start an exchange with. And so that's why neither 1 or 0 has any letters on them. And so they had 2 through 9, right, which is 8 numbers, and 3 characters per number gives you 24, and so they just left off Q. Because they figured there would be no exchanges that started with a Q. And so, this is the history of why there are letters around these numbers starting in the 1920s, when obviously they weren't thinking about, texting or anything like that. Right? Well, right. I mean, you can imagine uses for the Q. Squirrel Hill has a Q in it, right? It's not like the Q didn't exist in English, but in terms of which letter to leave out, it seems like it could have left out X or something, but... Oh, and Z too, right? Yeah. So Q and Z, they just left out. I don't know why. That would be interesting to research if somebody wanted to go back. It's really interesting. I was looking on Wikipedia for some of this stuff, and it's amazingly poor, the Wikipedia entries. And they really aren't linked to each other. So there's, one description of the, dial phones, which doesn't say anything about the letters, and another one that talks about the letters that's somewhere else, and they don't have the cross-links that they really should. So keypads for phones or dial phone, touch-tone phones came in the 60s. Because it was much faster, okay, but they're still using the same mechanism for exchanges. They're still having long distance in the operators in the same way. So phone numbers themselves haven't changed at all by the 60s. And so the keypad on the phone is basically identical to on the dial phone. So all the letters are on the same numbers. And when they designed the dial phone, they did a whole bunch of human factors research in order to see if people liked it and what orientation the buttons should be. And they tried all sorts of different orientations. And they came up with the one that we're all familiar with, where 1, 2, 3 is at the top. And interestingly, that's not the same way that calculators and number pads work, right? So if you look, if anybody has a number pad on their computer, you'll see that the numbers start with 1 at the bottom, whereas in phones they start with 1 at the top. And at the time, when they were doing this human factors research, most people weren't typists, right? You were just secretaries were the only people who typed in the 60s, right? There were no computers or anything like that that anybody had to deal with. And so it made sense to just say, what is the most natural? Which one do people like best? Totally independent of keyboards. And they decided that the people preferred the 1 at the top because they'd rather read down, across and down, than up, right? That reading up is kind of weird. So that's why the numbers are in that order on the phones and why they continue to be that order today. So, yeah, so they're the same today. Eventually, they added the star and the number sign, but for many years, those did nothing on phones anyway. They just kind of had the space for it, and they thought they would be used. They were used for business phones and, you know, to get your messages and some other special operations, but generally, they were kind of useless. So eventually, people got cell phones. Well, I guess I can do this. And they wanted to do text entry on them. And so these were phones that only had the regular keypad. And so how are you going to use them to do text entry? Well, we already had all these letters on the phones that people were used to. And so it was pretty natural to think about using them. But the problem is, of course, there's multiple letters on each number. So if I want a B, how do I type a B? And the straightforward way to say is, well, A is 1, 2, but B is 2 2s. So I type BB and then I get a 2. Or if I type, I type 2 2 and then I get a B. Or I type 2 2 2 and then I get a C, right? It's not very efficient. And certainly, you know, it's in alphabetical order and it doesn't have anything to do with which letters are most common, right? We know that the E is the most commonly typed letter, and that's two taps, which, you know, if you were doing this in the most optimal way, it wouldn't be. So if I want bet, I can just type 2 2 3 3 8, and that'll give me bet, okay? But suppose I want 2 characters from the same number. So if I want cab, I have to type C and then an A, right? So if I type 3 2s, that'll be a C, but then I have to wait for a little timeout. So it knows I'm ready for the next letter, and then I can type 2 again for the A, and then I have to wait in order for it to know that I'm done with the A, and then I can type the B with these 2 more 2s. So if I just typed 5 or 6 2s in a row, it would have no idea which order I wanted these in or how to separate them. And often people, sometimes one of these, I think like the star key or the number sign key, one of those would be the, okay, take it right away button. And so I don't remember which one it was, but you could type 2 2 2 and then one of those keys instead of waiting for the timeout. So when we think of, remember this keystrokes per character number that you can use to figure out how many keystrokes normally takes to enter things. The average for multi-tap is a little over 2. So on average, it takes about 2 taps to get whatever character it is you want when you're typing with multi-tap. And there's been a lot of study of how fast people were doing multi-tap, and it was typically around 10 to 12 words per minute, with some people getting as fast as up to 20. So we're still a long way from regular typing on a keyboard, but it's, you know, not ridiculous. It's certainly reasonable. So the next thing to come along is T9, and it's called T9 because it uses all 9 of the keys. And this is from a company called TGIC, which eventually was bought by a company called Nuance. So Nuance is kind of the big name in alternative entry these days. They also own a speech recognition mechanism, and they own the swipe character thing that some people have on their Android phones. So Nuance is a big player now. Anyway, the T9 idea was, let's let people just type a single character, and that character will represent all three of those letters, and then we'll figure out which one people probably meant at the end of the word. So if I wanted to type, cat, then I would just type 228. And there's a lot of different words that could be. It would try and predict which one is the most likely of all of the different combinations of the letters on the 2 key and the 8 key to see which one is most likely to be the one that I'd want to type. And if it guessed wrong, then you could type the star key, and that would give you other guesses. So I have a little video. And it was a little weird that as you're typing, it would change dynamically which keys were entered. This part's boring. Let's get to the actual typing. So he's turning this prediction on. And so as he types the keys, let's go. There we go. As he, I guess you can kind of see it up at the top. As he types the keys, then you get, it dynamically changes which ones it's guessing as he's typing it in. So you can see he's getting the different alternatives. And it also was a learning technique. So if you type, a name frequently, you could enter it into the dictionary, and it would use that more likely than others. This was measured at 15 words per minute, up to 40 words per minute. So we're getting to kind of the speed of typewriters now for expert users. And it's obviously a lot faster than multi-tap. And the measured keystrokes per character is almost down to 1. So that's pretty good. It's already helping you a lot compared to the other techniques. And this is a patented technique that they managed to keep, very active on. Jumping back to other devices besides phones, there were PDAs at the time, a lot of portable devices. These very first phones I talked about last time, the IBM Simon was probably the first PDA phone. It had a full screen phone, and it had a variety of kinds of keyboards on it that you could pick from if you wanted to type on the screen. But most systems of the time had these little keyboards. So this one is a fold-out keyboard. It's a really clunky big phone, the Nokia 9110. Kind of predates a lot of the stuff we're expecting now with these regular little keyboards. And that brings us to the Palm, and we talked about the Palm last time. It was about 96. It came out, and they didn't want to have this clunky keyboard, and so they also didn't want to have handwriting recognition that was unreliable, and so there were a variety of techniques you could use with the Palm Pilot. They did have a pop-up keyboard, so you could tap on the keys on the screen with the little stylus. And they had 3 keyboards by default: the regular keyboard, the number keyboard, and the international keyboard. Or you could use the graffiti language. And these gestures were designed to be single stroke, easy for the computer to recognize. But unlike quick writing that we saw before, they were designed to be really easy to learn. So they're supposed to look a lot like letters. So the A kind of looks like an uppercase A. The B kind of looks like an uppercase B. C looks like a C. D, E, F doesn't look anything like an F. So I guess a little bit. right? So some of the letters they kind of fudged on a little bit in order to make them fast and easy to enter. And there were usually other versions of these. So like there were 3 or 4 different E's you could draw if you didn't like the one that is the default one. So in the extended key set that you got with the machine, you could see that there's a whole bunch of different alternatives for a lot of these letters, and some of them were a little more flexible. And the numbers, in order to make it so you could draw a vertical bar for an I and a 1, they made it so you had to do it on different sides of the keyboard. So this is the letter side, and this is the number side, and so you'll notice that a 1 and an I are exactly the same stroke. And graffiti was measured at 16 or 18 words per minute. Wait, now the keyboard, let's see, novices, yeah. So novices with the keyboard, with the graffiti, were 7 words per minute compared to 16 with the keyboard. And experts did not get much faster with a keyboard. So experts were still 18 words per minute with the on-screen keyboard, but they got 3 times faster with graffiti. So typically, if you used a Palm Pilot, you got to use graffiti and you got pretty good at it, so you got to be a reasonably high speed. Anybody here use graffiti? A few people, yeah. So I used it for a number of years. Windows CE, if you remember, came out about the same time. It also had a pop-up keyboard. It had a version of handwriting that was very much like graffiti, but it was called Jot, slightly different alphabet. They also had versions with little keyboards. Nothing very interesting there. The Blackberries, we talked about before, came out with these cute little keyboards, which were generally considered to be thumb keyboards. You're supposed to use them with 2 thumbs. And that's kind of different than these keyboards, which were kind of assumed to be used on a desk, right? So a keyboard like this, you probably are not going to use in the air. You're probably going to put it down on something and use it kind of like a regular keyboard. And that was true of most of the previous keyboards, like this one and stuff like that. Where the on-screen keyboards, you were generally assumed to be holding the device with one hand and have the stylus in the other hand, and so you're hunting and pecking with one hand, right? So it was a pretty big deal that the RIM had this idea that you could use 2 hands, 2 fingers, 2 thumbs in particular, to use this device, and that you'd use it in the air. You could certainly do it with one hand if you wanted to, but it was a 2-thumb keyboard. And the idea of having a keyboard on a device was obviously not new, but what they do have a bunch of patents on is the idea of rotating all the keys around this circle like this so that they're more efficient to hit with your 2 thumbs. And if you think about your thumbs moving, they're going to move in an arc, and that's kind of the way the keys are laid out. Right? So these are optimized, even on the later models, for hitting with your thumbs in an easy way. And they're still in the QWERTY layout from a regular keyboard, so it's easy to learn. 2-thumb typing starts off pretty fast and gets really fast. So people learn to type quite fast with their thumbs. There's really no way to use this with all your fingers, right? So the most you could probably use are 2 thumbs. But it's still pretty, it still can get pretty fast. Eventually, RIM had a new device with 2 characters per key. So it's kind of using the T9 technique of predicting what you want, right? So that this one key is both E and R. So in T9 in a regular key set, you have 3 or 4 characters per key, whereas here you only have 2, so it's a little easier to predict. Never caught on. It was kind of a silly thing to do. I wanted to bring up Twiddler, which I didn't mention before, because it's probably the fastest one-handed input technique. And it's quite old. It's from the 90s. And it was invented for wearable computers and things like that when you're on the go, or you want to have your other hand doing something. And it's a chord keyboard, so it has it's kind of like for court reporters that we saw before, where you're pushing in multiple fingers at the same time. And this is Thad Starner, who, I don't know if you were here, he came and gave a visit. He works for Google now, and he's the key person behind Google Glasses, which is a wearable computer. But he's been doing wearable computers since he was a PhD student at the MIT Media Lab. And he really likes this device. He probably was using it when he was here. He claims that he personally can get to be, I didn't put it on the slide. Oh yeah, here it is, 60 words per minute using that device. And they've quoted him on the Twiddler website because he's a famous guy that uses it a lot. But they also did some measurement that showed that novices are kind of like zero because it's really hard to learn to use. So they finally got novices up to 10 words per minute with a weekend's worth of practice. So, you kind of start off really low with this device, and you can't do anything until you practice at least a weekend. And still you get pretty low. But, if you wanted to train yourself to do this, you could theoretically get to be really fast with it for your portable devices. Windows tablet PCs, not very interesting. They have text entry just like the other ones. And that brings us to the iPhone, which was really a very radical departure. So all the previous stuff had been done for styluses, right? And here all of a sudden we're trying to make it so you can do it with your finger. It's a capacitive screen, so you can touch two things at once, but it doesn't recognize a stylus at all. So the stylus techniques are not even possible. And so they have this on-screen keyboard. One of the problems with your finger, of course, is your finger is opaque and you can't see through it, and it's kind of big. And so the problem with the keyboard is that you're covering up the letter you're pressing on, and so you can't see where you're pressing. And so they came up with this idea of having these pop-up little tabs to show you what letter you're on. And how many people knew that if you held down, you would get alternate letters? Probably all the foreign students do, right? So if you wanted to get Enye, you push down on the N, and it pops up a bunch of choices, right? Or this is U with all the different umlauts and other kinds of accents on it. So most of the letters will pop up alternatives if you press on them and hold down. So that's one invention. The other invention is it was the first device to take the autocorrects by default. All previous systems that I'm aware of made you pick whether you wanted to use the autocorrects or the auto predictions explicitly, whereas on the iPhone it does it, well, it actually does autocorrect by default, but if you wanted to use the auto prediction, then you have to confirm it by typing a space, right? So if you wanted whatchamacallit at this point, if you type a space, it will use this, and if you type a different letter, then it will see if the different letter is consistent with what you're trying to type. Another thing that you can't really see and you may not know about the keyboard is that they actually have a very sophisticated algorithm going on behind the scenes that's trying to predict which letter you most likely are going to type next. And it makes the target area for that letter a little bigger, right? So if it thinks there's a high likelihood I'm going to type an A and very little likelihood I'm going to type an S, then the area for A will actually get bigger and may even include some of the S. And so if you hit in exactly the same place, depending on what your context is, it may do something slightly different. And it's really hard to tell because obviously it's just doing the right thing. But it is part of the algorithm that's going on behind the scenes. So there's a surprising amount of sophistication going on, like most of the stuff that Apple has done in the iPhone, in order to try and make this work better than maybe than you would expect. So there's been a lot of research on the idea of soft keyboards on the screen, and so I'm going to try and cover a few research systems in the little time that's left. One idea is there's no particular reason to have them in QWERTY order, right? That's just historical accident left over from these mechanical typewriters, right? And so suppose you reordered them differently. And there's been a lot of research that shows that, sure enough, that would be a lot faster. And so this is called the Opti layout. It's by Scott McKenzie, who we saw before. and one of his former students. And he has multiple space bars, because it turns out space, remember I said backspace was the second most popular key? Well, the most is space, because you type that every 5 characters, no matter what you're doing. So he has 4 space bars here. He doesn't have any backspaces, so that's a little weird. But this layout, and notice that things like the are right next to each other, right? Or that, right? So it's optimized in order to put the letters you're most likely to use together right next to each other. He did this by trial and error, but he had behind the scenes a mathematical model that, given a layout, would tell you for all the most common, whatever, 50,000 English words, how fast it would be to type them. And so you can imagine if you had 10,000, 50,000 words, it could measure how long it takes to move, right? So remember Fitts' law and all of those algorithms we had about how long it takes people to move, depending on how big the targets are. Well, he used all that math in order to calculate the maximum possible speed given an expert trying to move around these keys. And so he predicted that it could be much faster. And then he did an actual experiment with people. And you would expect that, as you would expect, the QWERTY one, which is the top one, is faster at the beginning because people are used to it. And if you're trying to type here and you're saying, okay, I want a G, then you're going to have to look around and see if you can find it. Oh, here it is, right? So that's going to be a lot slower. Whereas on a QWERTY keyboard, you might remember where it is. So QWERTY started off faster, but about the, I guess, maybe 12th session, at that point, this got to be faster, and it ended up at the end of 20 sessions, which is all they did. At the end of 20 sessions, it was 45 words per minute compared to 40 for QWERTY, and they extended it out, and they predicted that at 50 sessions, it would be as much as 60 words per minute, right? So it seems like this would be a lot faster if only people would be willing to spend at least 20 sessions, or whatever, 20 sessions learning how to use it. But he did that layout by trial and error. So Schumann Zai, who was at IBM, said, we can do better than that. Let's use an algorithm to optimize the layout automatically. And so he wrote an optimization algorithm that computed the optimum layout based on the English, the same English corpus. And also he said, there's no reason to make the keys square on the screen. So he made them into hexagons. And because that means that it adds a little bit of extra space that makes these closer together on the diagonals. So if I want to go in the diagonal direction, which is just as common as horizontal or vertical, a hexagon means they're closer. And it's slightly better. Remember before we saw 40-ish words per minute, and this one is at 43, so that's slightly better. And if you go to the literature, the research literature, or the or commercial products, you can actually buy other layouts today for your devices. There are an awful lot of different ones in the same way. And the last thing it's really important to cover is ShapeWriter, which was originally called Shark. Schumann Zai, which is the same guy as the keyboards, came up with this idea of just drawing the shapes on top of the characters. So he did it over one of his optimized characters. So this is, I forget what letters these are, but just by drawing your shapes. And the original idea was he just used a shape recognizer, which wasn't particularly accurate. So then in a later version, he took into account the shape and what letters you were on top of, which seems pretty obvious as a way to do it. And eventually he was able to show he was getting up to 50 to 80 words per minute as you're drawing these shapes really quickly. And they formed a little startup called ShapeWriter. And there's a version of it for the iPhone and a bunch of other things. In parallel, apparently, this company called Swipe did the same thing. And there's actually 3 or 4 other companies that did the same thing. But IBM had the patent first. And so they started suing everybody. And so what eventually ended up happening is Nuance, remember that company we talked about before that had T9, bought both of these. So they bought the ShapeWriter company and its patents, and they bought the Swipe company and its patents. So now Nuance owns the patents, and they own 2 different technologies to implement it. And if you're using this swipe mechanism on your Samsung phones, then this is the version that you're using. So it originally came out of an academic researcher working at IBM, improved through the years with a variety of algorithms. And there's a bunch of other researchy systems. Siren was done by our colleagues upstairs. Jen Mankoff and she did it because she had RSI, and it was hard to use a keyboard, and so she wanted to just swoop around, and so she made the circle thing, and so this is finished. F-I-N-I-S-H, where the E-D, right? So you could just pass over letters, and as you passed over them, it would type them. She got to about 20 words per minute. And then my student and I did a system called EdgeWrite, which was a really interesting idea. First, we started putting the letters around the outside of the iPhone. The idea was to help people who had tremors, whose hands were shaky, either because they had a muscular dystrophy, which gives you very little control over your limbs, and so they can't move very well, or Parkinson's disease, where you actually have a tremor. And so the thought was that if you could bash against the edges of the screen, maybe that would be more accurate. So we tried putting them around the outside, and that was really slow. So the second idea was to build a little plastic insert, and then you would just hit the corners of this plastic insert with your stylus. And so there were holes, because if you remember, there are menus here. So you want to click on the menus. So that's what these were for, but you could do all of your characters just by clicking from corner to corner. And part of the design was that if you didn't go to a corner, it didn't matter what path you did. So if you were shaky, that was fine, as long as you hit a corner and you could be shaky and then you hit another corner. So the corners would make you stop. And so again, like graffiti, all the letters kind of look like they're equivalent. So B is kind of like a B. C, D is like a D. And so the idea was that these would be easy to recognize. And again, we had different versions of each letter. So that was the general idea. The loops, like this loop in the B, you didn't really draw that. You actually went back and forth along the bottom. But we just drew the loop in the representation to make it clearer what you're supposed to do. And one of the things that we noticed is that none of the letters ended up in the upper left corner. That when the natural design for every letter, for some reason, it's not too surprising, because in English you're kind of going left to right. And so you kind of, not too surprising that most of the letters end up on the right instead of on the left. And the ones that do end up on the right or on the left tend to end up in the bottom. So we said, let's reserve the upper left corner for capitals. So rather than having a mode, if I want an A, I do this, and if I want a capital A, I go up here to the top left and stop when I'm done. So A or capital A is kind of the same gesture with a little piece on it on. And then we also added a word prediction version of this, where after you did a letter, it would give you 4 choices for words. And it was amazing how accurate that was. That based on one character, 50% of the time you could get the word you wanted if it was one of 4. And after 4 characters, you got to like 98% of all the words. So the idea was that you typed a few letters and then you would get the word that you wanted. And the way you signaled that was either by making a little, what's called a pigtail, a little loop, or exiting a corner and re-entering the same corner. So none of the letter designs use the same corner over again. You always went from one corner to another corner. So we used re-entering the same corner as a signal. And Jake personally was able to get up to like 24 or 63 words per minute, pretty amazingly fast with this technique. But it was really designed for handicapped people, and they could get surprisingly fast too. So they were at like 12 or 8 words per minute. And these are people who can't use a regular keyboard because of their physical disabilities. And we implemented EdgeWrite on a large number of devices, not just on styluses. So we did it on trackballs and styluses and joysticks. We even did it on the back of a phone with a joystick. So this was the idea was that you could use this backwards. So as you're holding the phone, you could do it with your index finger on the same hand, so you wouldn't need your other hand at all. And the interesting question was, would it be backwards? Would people expect to draw the letters backwards? So we did a little study and said, no, people are going to expect to do it as if they're looking through the phone at their finger. So if your finger, if you draw a C, which way would you draw it? Well, you'd have to draw it backwards in order to see it the right way, and that's what people tended to do. It was only 8 to 9 words per minute, drawing on the back of the phone, but still it was kind of fun.
It seems like all the devices you tried on are super ancient.
Yeah, well, obviously we did this work in 2006. So there's an implementation for the iPhone. I don't know if there's one for Android. It would definitely be fun to recreate some of this. And if you're interested, that would definitely be a great project. Okay, obviously we run out of time. There's a lot of other techniques. Chris Harrison is going to come and give a guest lecture, and he'll probably talk about his technique. There's a layout for iPhones that's optimized for 2 thumbs that pulls the keyboard apart. And so there were at least 5 papers on different optimizations for keys at the last CHI conference. I didn't even look at this year's conference, but there's probably a bunch more. So this is still a really active area of research. And if anybody's interested in, hopefully when you're doing the homework, you can find some interesting devices to do text entry with. And, if you have an Android phone, you can, download some of these alternatives. On iPhones, you don't really have much choices. But there should be some fun things to try. Okay. Sorry I went over. There's a bunch of old exams and one homework here to pick up.